So solution concentrations. We can use qualitative descriptions, dilute or concentrated, and these mean exactly what you think they mean. Dilute means there's not very much solute, small quantities of solute relative to the amount of solvent, and concentrated means there's large quantities of solute relative to the solvent. And so those are useful, but then there's also a lot of quantitative measurements. And there are so many different quantitative measures of concentration because they are useful in different situations. There's a bunch of them. So this is a helpful table in your textbook that lists some of the more common ones used in chemistry. Molarity, we learned about back in chapter 5. That's the amount of solute in moles divided by the volume of solution in liters. And that's the most common concentration unit used in chemistry. But there are others. There's molality, which is not a misspelling of molarity. There's mole fraction, mole percent, parts by mass. So parts by mass, this is looking at the part over the whole. So the mass of the solute divided by the mass of the whole solution, and then multiplying it by a factor. And the factor that you multiply it by depends on what is convenient, what gives a convenient number. So percent is the part over the whole times 100. So the multiplication factor is 100. You can also have parts per million, parts per billion. You could go parts per trillion. And here you're multiplying by a million or by a billion. And you would use those units when your concentration is small. So that instead of having 0.000006%, you might have 6 parts per billion. And then you can also do parts by volume. And again, you can have percent, parts per million, parts per billion. But here you've got the volume of solute divided by the volume of solution times a factor. And then another one that's not listed here is mass volume. So you can look at the mass of solute divided by the volume of solution multiplied by a factor. So quick review of molarity. It says see also section 5.2. We're looking at the amount of solute in moles divided by the volume of solution in liters, and we have to use those units. Here we have an illustration of how to make a 1 molar solution of sodium chloride. That's going to have 1 mole of sodium chloride dissolved in 1 liter of solution. Molarity is going to change slightly with temperature. It will decrease slightly as you increase the temperature because when you warm a liquid, its density changes. The volume becomes larger, and if the volume changes, the amount of solute doesn't change, the number of moles doesn't change, but the solution becomes larger in volume, and so that causes the molarity to decrease slightly. Most of the time, that's just really not an issue. But molality is a similar unit, but is not dependent on temperature. So molality is, again, the amount of solute in moles, but now instead of dividing by the volume of solution, we're dividing by the mass of the solvent in kilograms. And if this is water, a kilogram of water is a liter of water. And so molality and molarity values will be similar. Molality is used, though, where we need something that's not dependent on temperature. Molality, for the most part, I think is a pretty worthless unit. But we do have to use it when we're looking at temperature changes, and so we do have to acknowledge its existence. The abbreviation for it is a lowercase italicized m, not to be confused with a non-italicized lowercase m, which is the meter, right? So molarity is a capital M, molality is a lowercase m. Not confusing at all, right? Yeah, it is. Parts by mass and parts by volume. It's the parts that you're interested in divided by how many total parts. So like if you're talking about percentage of people, if you've got 3 people in a group of 10 people, see, three guys in a group of 10 people, right? So the part would be the 3 guys, and the whole thing would be the total number of people. Parts by mass just says that we're looking at the mass of the things. So mass of solute divided by the mass of solution times a factor. Percent literally means per 100. Parts per billion is per billion, and so that's what you're multiplying by. Multiplying by 100, by a billion, by a million. And then we can take that percentage or parts per million, like 14%, and that literally means 14 parts per 100 parts. So if it's mass, we can use whatever mass unit is convenient. 14 grams of solute per 100 grams of solution. You could do that with pounds if you wanted to, or kilograms or micrograms or whatever is useful. Parts per million, multiplying by a million. Parts per billion, multiplying by a billion. So when we see 15 parts per billion, that means there are 15 parts, 15 grams of solute per billion grams of solution. A very, very low concentration. Parts by volume, same pattern. So 22% ethanol by volume. 22, use your favorite volume unit, ethanol, per 100, same volume unit of solution. So 22 milliliters per 100 milliliters. So then we can do some problems. What mass of sucrose in grams is contained in 55 milliliters of a soft drink that is 11.5% sucrose by mass, assume a density of 1.04 grams per milliliter? So these really are unit conversion problems, but we have to recognize what the different units mean. So we've got some numbers in here. This 12 ounces here in parentheses is just sort of an aside because 355 milliliters probably doesn't mean much to you. This is a 12 ounce can of soda. So we've got 355 milliliters, and we've got 11.5% sucrose. Well, what does 11.5% mean? 11.5 per 100. 11.5 per 100. And we're told that it's by mass. So an easy unit to use here would be gram, especially since we're looking for an answer in grams. That means there's 11.5 grams of sucrose in 100 grams of solution, soda. It's a mixture of the water and the sugar. Does that look like a conversion factor? Yeah, that's our conversion factor. We also have a density given here. We could write that down, 1.04 grams. Make that a vertical fraction. What's that the density of? Is that the density of sucrose or water? It's the density of the soda, right? So there's 1.04 grams of soda per per milliliter of soda. It's just a little more dense than water. So I pulled the numbers out. Again, it's always a decent approach to say, well, could I do this using dimensional analysis? Sometimes you can't, but it never hurts to look. This one we can. So what am I trying to find? I have to make a path. Question is, what mass of sucrose in grams? So I'm trying to find grams of sucrose. That's where I'm going. And then where am I going to start? I've got 3 numbers here, and 2 of them have per units, right? These could be conversion factors. So I'm probably going to start with this 355 milliliters. That's 355 milliliters of what? of the soda, right? So let's go back up there and label that. So I'm trying to, I left off the unit down here. That's no good. So 355 milliliters of soda, and I'm trying to get to grams of sucrose. Well, I'm going to look at these conversion factors that I was provided with and see what I can do here. I'm starting with milliliters of soda. This density here would allow me to convert to grams of soda. And then the concentration in percent gives me the relationship between grams of sucrose and grams of soda, and it turns out that's that last step that I need. So I've identified the path I need to take. That's the hard part. And now we follow the same pattern we learned at the beginning of the semester. I've got two arrows. I'm going to have two fractions, and I follow the path of units for the numerator, and then I put in the denominator units so they cancel out. So 55 milliliters of soda times a line. This is going to be grams of soda. So I'm just following my path. Times in a line, and this time I've got grams of sucrose. And that's my last one. So this unit here, milliliters of soda, is going to be in the denominator here. So the units cancel out. And grams of soda goes down here. So the units cancel out. Once I get all the units in place, then I can look for the numbers. Here where I have grams of sucrose and grams of soda, that's this one here. 11.5 grams of sucrose. Grams of sucrose is on the top, so the 11.5 goes on the top. 100 grams of soda goes on the other side of the line. And then this density, 1.04 grams of soda. So that's over here, 1.04 grams of soda per 1 milliliter of soda. Any questions? It's not too late to figure this out. Right? Some of you are still a little iffy on it. It really is a very, very useful technique. You can bluff your way through a lot of calculations with it. 355 times 1.04 times 11.5 divided by 100. And my calculator is showing me 42.458. And that would be grams of sucrose. And then we should always do our best with significant figures. 355 milliliters of soda, that's a measurement. It's not an exact number. 3 sig figs. Density, 3 sig figs. The percentage here, 3 sig figs. When we say per 100, the 100 is exact. It's by definition. But the 11.5 is not exact. So 3 sig figs there. So I should keep 3 significant figures in my answer. And I'm going to say there's 42.5 grams of sucrose in that can of soda. Any questions? Here's another one. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 ppb by mass, that's parts per billion. What volume of this water contains 5.00 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1 gram per milliliter. Well, pull the numbers out, write them down. 15 ppb. So 15 ppb means 15 parts per billion parts. That's 10 to the 9. And this is by mass. So probably grams. 15 grams per billion grams of the solution. Here the solution is the water containing the chlorobenzene, I'm going to call it solution so that we don't think it's the solvent. And this is the chlorobenzene. And then we've got this number 5.00 times 10 to the 2 milligrams of chlorobenzene. And we're given a density, 1.00 grams per milliliter. And what's that the density of? The water containing the chlorobenzene. So we're calling it solution. You have a question in the back?
You put grams on parts per million. I know that. How are we 100% sure it's grams? I mean,
That's an excellent question. We could use lots of different mass units there. We could look at this and say, well, I've got 5 times 10 to the 2 milligrams. I'm going to use milligrams per milligram. 15 milligrams per billion milligrams. That works as well, right? But then I'm also looking ahead and saying that this is grams per milliliter. And so I'm thinking I'm probably going to need grams in there somewhere. So I'll just kind of default to grams here. But it doesn't matter what unit you use here. It just needs to be the same on the top and the bottom because they cancel out. Yeah. Okay, so those are all the values given. And again, we've got one number that has a single unit, and the others look like conversion factors, right? They've got per, this per that. So this is our per, our concentration, and this density, grams per milliliter. So I'm probably going to start with that milligrams of chlorobenzene. So 5.00 times 10 to the 2 milligrams of the chlorobenzene. And what am I trying to find? Volume of water. And the water, we're calling this solution because it has the chlorobenzene in it, right? Teeny, teeny, tiny bit. I'm asked for a volume, and it doesn't specify the unit. What would be an easy unit? Milliliters, because I've got the density there in milliliters, so I'm just going to find this in milliliters of water. Okay? So now I need to figure out how can I get from milligrams of chlorobenzene to milliliters of water. And if I look over here, I don't see milligrams of chlorobenzene. I used this one already. Here I don't have milligrams, I have grams. But can we convert milligrams to grams? Sure, that should be pretty easy. So I could convert this to grams of chlorobenzene. Just using my knowledge of metric prefixes. And then this is the relationship between grams of chlorobenzene and grams of solution. So I could go to grams of solution. And then my density is grams of solution to milliliters of solution. On the last slide, on this slide, this is not the only way to solve this problem, but it's using this technique and just following a pattern, and even if it's not exactly the fastest all the time, if it's familiar and straightforward and it gives you the right answer, that's better than fast and maybe getting the wrong answer. So if you're good with units and percentages and things and you can think about this in a different way, go for it. But however you do it, you should be able to write it down so that someone else looking at it who knows about units can figure out what you did. That would be me. So I can figure out what you were doing, okay? So I have 3 arrows this time. And I'm tired of writing chlorobenzene, so I'm going to call that Cb. So 5.00 times 10 to the 2 milligrams of chlorobenzene, and then an arrow, and the next unit is grams of chlorobenzene. And then I'm going to grams of solution. And then I'm going to milliliters of solution. For the denominator, I'm just going to take this first unit and put it in the denominator so they cancel out. And the grams go down here. And the other grams go down here. In my concentration, 15 grams of chlorobenzene per billion grams of solution. I'm going to look at the factor that has grams of solution and grams of chlorobenzene. And in front of grams of chlorobenzene was 15, so I'm going to put 15 there. And billion was the grams of solution. I'm going to add a 1 times so that I don't have to wonder what should I do with that on my calculator. So 1 times 10 to the 9th. My density was 1 gram of solution per milliliter. So I've got 1 gram of solution per 1 milliliter of solution. And then here I need to know what milli means. And milli stands for times 10 to the minus third. So I've got gram on top and gram on the bottom. I've got milli on the bottom. I want to put what milli means on the top. 10 to the minus 3. So 1 milligram is 1 times 10 to the minus 3 grams. Make sure that you are comfortable with scientific notation on your calculator, because sometimes I'm still seeing a setup like this that's correct, but then your answer is off by factors of 10 because you're miscommunicating with your calculator. So remember, the EE button stands for times 10 to that. So 5 EE2 times 1 EE negative 3 times 1 EE9 divided by 15 times 1 divided by 1. And my calculator is giving me a whole bunch of 3's, and I don't really want to look at that, so I'm going to tell it to give it to me in scientific notation. Most calculators will do that conversion for you, and I would encourage you to learn how to do that, because I'm also still seeing people getting the sign wrong. And so this should be, we should have, how many sig figs? 2. This one's 3, and that's exact. This billion is exact, but this is only 2. And then here we've got 3. So 2 sig figs, 3.3 times 10 to the 7th milliliters is the answer.
How do you do that on the calculator?
So on the TI-36X Pro, up at the top there's a mode button. So press mode, and it'll give you a bunch of choices. And you want to ignore the radians, degree, grads thing. Go down, it says norm, psi, or eng. So scientific notation, you go over there and you press the enter button. Now you're like, now what do I do? Well, then you want to quit. So second, and that same mode button again. And you're like, but where's my number? Just press the enter button and it'll come back. We should know how to do it without the calculator, but you have the calculator, you might as well get it right. Yeah. Again, this is a big number, and a big number gives me positive feelings because I have positive feelings about large paychecks. This would be a great paycheck, right? Any questions? .3 times 10 to the 4 liters. Are those the same? Yeah, they are. Let's just double check. So I gave the answer in milliliters because I thought that'd be easy. And then it's wanting it in liters apparently, so I can convert that. We put milliliters on the bottom, liters on top. 1 milliliter is 1 times 10 to the minus third liters. Milliliters cancel out. And that's 3.3 times 10 to the 4 liters. Okay? So on to some other ones. Mole fraction and mole percent. So we're familiar with percent, right? It's the part over the whole times 100. The part over the whole is the fraction. A percent is a fraction times 100. So here, the mole fraction is the moles of solute divided by the total number of moles of solution. So that would be the total moles of solute and the moles of solvent. That's the mole fraction, and that's given the symbol Greek letter chi. So chi solute is the mole fraction of the solute. So that's going to equal the number of moles of solute divided by the number of moles of solute plus the number of moles of solvent. If we want the percent, we've got that, the part over the whole, and we just multiply by 100 to give it a percent. So here's a fun one that has us do a lot of different calculations. So a solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. Molarity, mole fraction, molality, mole percent, and percent by mass. Let's just start at the top. So molarity, what's the definition of molarity? It's moles per liter, right? So this is moles of solute. Here the solute is sucrose per liter of solution. So we need to find the moles of sucrose and we need the liters of solution. Well, they gave us a mass of sucrose, but we can convert mass to moles. They also gave us the formula, so that's nice. So 50.4 grams of C12H22O11. We need to know how many moles that is. So we're going to divide by grams, and we're going to need the molar mass. So 12 times the mass of carbon is 12.01, plus 22 times the mass of hydrogen, 1.008, plus 11 times the mass of oxygen is 16, gives me 3, 4, 2, no, I don't want it in scientific notation. I'll go with 342.3 grams. This one has 3 significant figures here. Keeping one extra is probably good enough. So 50.4 divided by 342.3. 0.1472 moles. So that's the moles of sucrose. So I can plug that in. 0.1472 moles of sucrose. Divided by the volume of solution in liters. Well, they gave me milliliters. So 355 milliliters. Many of you are okay with just doing this one in your head, but some of you are going to do it backwards, so don't. Liters on top, milliliters on the bottom. 1 times 10 minus 3, 1. And so this is 0.355 liters. If you don't want to write it out, but you want to make sure that you get the direction correct, Think about glassware that we've used in lab. How big is a 1 liter flask? It's fairly big, right? It's about the size of a half of a 2 liter bottle of soda, strangely. And how big is a milliliter? Think about that 10 mil graduated cylinder, a milliliter, about that big, right? It's a cubic centimeter. So if I have 355 milliliters, does that mean I have 355,000 liters? Nope, that's the wrong way. Okay? So you can use a little common sense and make sure that you're getting that direction correct. So 355 milliliters is 0.355 liters. And so I've got 0.1472 divided by 0.355. And that's going to give me 0.4146. And for my final answer, I'll round that to 3 significant figures, 0.415 capital M. That's the molarity of the solution. And if I screw it up, please yell. Just going to make some space here because I need to do another calculation. Okay, mole fraction. What's the definition of mole fraction? It's a percentage without the 100, and it's moles. So it's the moles of the part divided by the moles of the whole thing. So this is going to be equal to, I'm going to do a different color here so they don't get so mixed up. Moles of sucrose divided by moles of the whole thing. Well, I can't calculate directly the moles of the whole thing. I have to add them together. So I've got moles of sucrose plus moles of the solvent, which here is water. Well, do I know how many moles of sucrose I have? Yeah, because I already did that calculation. So it's right up here. So I have 0.1472 moles of sucrose, and then down here, got 0.1472 moles of sucrose, plus I need to figure out how many moles of water do I have. Well, I've got the volume of the solution, but that doesn't help me out here. But they did tell me the mass of water in kilograms. So I can convert that into moles. So 0.332 kilograms of water. I need to change that into grams of water. So kilograms on the bottom, grams on the top. 1 kilogram is 1 times 10 to the 3 grams. And then I'm going to need the molar mass of water, which is 18.02 grams per mole. And so this is giving me 18.42 moles of water. Anybody else get that? Okay. So that's moles of water. So I'm going to put that here in the denominator. 18.42 moles of water. So the total moles of the solution is the moles of the water plus the moles of the sugar. So I can do this in one step on my calculator, but I need to be careful. So I've got my numerator divided by, and then I'm going to open parentheses, 0.1472 plus 18.42, close parentheses, equals, I get 0.007 9279. And what's the unit on that? There is no unit. I've got moles divided by moles. Those units go away. So 0.00793 is the mole fraction. Mole fraction has to be less than 1 because the part can't be more than the whole thing. Molality. What's molality? A weird one. It's moles of solute, so moles of sucrose, divided by kilograms of solvent. Not kilograms of solution, kilograms of solvent. So here our solvent is water. So this one, because of previous calculations we had to do, is going to be fairly simple. We already have our moles of sucrose, 0.1472 moles, divided by kilograms of water, which they gave us, 0.332 kilograms. Zero 0.44337 moles per kilogram. 0.443 lowercase m, not meter, molality. Those lowercase m's can be confusing, but usually if you look at context, it's pretty simple to figure out that I don't mean that the concentration is 0.443 meters, right? Because that's not a concentration unit. Questions about that one? Okay, mole percent. What's the mole percent defined as? Mole fraction times 100, right? So the mole fraction times 100. Well, we already figured out the mole fraction, right? 0.0079279. So I'm going to multiply by 100, and that's going to give me percent, so 0.79279%. Or rounding for significant figures, 0.793%. How about percent by mass? Percent is the part over the whole, and here mass. So we can use kilograms or we could use grams, whichever is more convenient. Kind of like grams. So this is going to be grams of sucrose divided by grams of solution times 100% by mass. Well, grams of solution is 50.4. I'm sorry, grams of sucrose is 50.4. What's the mass of the whole solution? Do we have that written out anywhere? No, we don't. But do we have the mass of the solute and the mass of the solution? I mean, mass of the solvent? Yeah, we do. So 50.4 grams is the solute, the sucrose, and the mass of the water, we had 0.332 kilograms. That's 332 grams. You could write that out. 50.4 divided by, open parentheses, 50.4 plus 332, close parentheses, times 100. 13.1799%, 3 sig figs, 13.2%. Any questions? The information that you need for things like mole fraction or molality may be different than the information you need for molarity. Because for the molarity, we just needed the solution volume, right? We didn't need the mass of water. But we did need the mass of water to find moles for mole fraction or the mass of water for molality. And so that's why they gave us so much information there, so we could do all of these. So let's see if I got those right. Yeah, I think so. They're out of order though. I'll have to fix that. So we should be able to convert between different concentration units. So here, what's the molarity of a 10.5% by mass solution? Again, we can approach this as unit analysis, dimensional analysis. Let's write down the numbers and see what we can do with them. 10.5% by mass means 10.5 grams per 100 grams. And that would be grams of glucose, C6H12O6, per 100 grams of solution. And we have a density. The density is 1.03 grams per milliliter. That's the density of the solution, so that's grams of solution divided by volume of solution. So what seems to be missing here? A starting number, right? Normally we'd have like these per units that we're supposed to use as conversion factors, but then there'd be a number like 355 milliliters that would tell us, okay, we start with this and we convert it to something else. Here we're going from one concentration unit to another concentration unit. The concentration doesn't depend on how much of the solution we have. So there is no starting number here. And so that can be disturbing. So there's two approaches. We can take this concentration and change the numerator and the denominator as needed to get what we want. We're trying to find molarity, right? So molarity is moles of... Is that telephone ringing? We'll just ignore it. Nobody should be calling classrooms. Per liter of solution. So we could convert the numerator from grams to moles and the denominator from grams to liters. In my experience, students find that a little confusing because it's just an added step and it's just enough just to do the unit analysis, right? So what else could we do? Well, we can do essentially the same thing, but separated so it's less confusing. This is my concentration. I can take the 10.5 grams of sucrose and convert to moles and just figure out what that is. And I can take my 100 grams of solution and convert to liters and write that down and figure out what it is. And then I can put the two together for the molarity. So that's what we're going to do. Because the people who can do this one can do it without me showing them how. So I'm going to take the 10.5 grams of glucose, and I'm going to convert to moles, just by itself. So I want moles of sucrose on the top and grams, sorry, not sucrose, glucose on the bottom. And so for this, I need the molar mass of glucose, which, one of these years I'll get that memorized, but not just yet. 6 times 12.01 plus 12 times 1.008 plus 6 times 16. Syntax error. Great. 180.156. So 1 mole, 180.2. So 10.5 divided by 180.2 is going to be 0.058. There's my 3 sig figs, 68 moles. And then separately, I'm going to take my 100 grams of solution and convert to liters. So I'm going to have to go to milliliters first and then to liters. So grams of solution is going to cancel out, and milliliters will cancel out. The density was 1.03, so 1.03 grams of solution is 1 milliliter. And then here I'm using my metric conversions. So 100 divided by 1.03 times 1 times 10 to the minus 3. 0.097 0.087 liters. The 100 grams is exact because it came from this pointers. That 100 grams is from up here, so that's exact, but my density is not exact, so this would have 3 significant figures. So molarity then is the moles, 0.058268 moles, divided by the volume in liters, 0.097087 liters. Any questions? .6.